Hi everyone, in this video, I'm going to be talking about the derivative as it's applied to, for example, deep learning. Um, Now, derivative is important in the field like deep learning is because a lot of time in deep learning, we want to maximize a model, or another way to say that is we want to minimize the error function. And the error function, the way to minimize that is we need to know how the path of the function is moving. Is it increasing or decreasing? And the derivative tell us about that. Essentially, the derivative show how a function changes with respect to the horizontal variable. And you can think of derivative as the slope of the function at each point right there. So with derivative and you had the error function, um, uh, it can tell the direction, the path that you need to follow in order to minimize the error. In other words, maximize the value for the model right here. In order to uh, in order to do derivative in Colab and Python, we also need to import the SymPy library right here. This one right here is a plotting simplot that we can use to plot the function created from SymPy. Now you can see right here, right? Just for an example, a polynomial. The derivative of a polynomial function is defined as this right here. So if the polynomial has the x to the n power, then derivative is n to the minus 1, and you bring n down here. And I created function formula using latex in between the two money symbol right here, as you can see, with the text cell. So to create a function in SymPy, we need to define the symbol first, right here, using the symbol function in SymPy to define x. And then after that, we create the function, and this one right here is 7 times x to the third power. And to differentiate, to find the derivative of that, we use the diff function right here. We pass in the symbol and the function. And then here we'll print it out, the function and the derivative. This plot right here is just going to plot the function and the derivative for -5 to 5 right here. And then here's a title for each of the plot. Okay, so if I run this, you see that it's going to give us the function, the derivative, and the plot of the function and the plot of the derivative right here. You can see over here it's increasing slowly and then faster. So the slope is going to be positive. The slope is going to be positive, and and incline steeper right there. And then you can see right here, right, it's approaching zero. It's approaching zero, and it's decreasing. It's increasing to zero in this situation right here too, but slowing down the pace of the pace of decreasing. So that's why you see the slope is become less and less and approaching zero right there. Okay, and then another few example, and for derivative is a sigmoid function and the Relu function. They are important because they are used many times in the neural network as activation function. Okay, now activation function is if you have an input, right, and you have a weighted node right there, the activation function would transform the input and according to the weight, and the activation function here acts as a transformation, and it's usually the sigmoid or the Relu function right here. Okay. Now this right here is is the graph of the sigmoid function using the matplotlib right here, and that here's a formula for the sigmoid function. Uh, Basically, it's 1 over this entire expression right here, exponential to the minus x. Okay, so we plot that. You can see right there, it kind of horizontal like this, increasing into 0, and then kind of tapering off at 1 right here. Okay, and here is the derivative of the sigmoid function. It's basically the derivative of that is just sigmoid times 1 minus sigmoid right here. So if you plot it, you can see that it's kind of have a normal Gaussian distribution right here. One thing you also want to notice is that the maximum number of the derivative is 0.25, right, compared to the sigmoid right here, which is 1. So if you plot it on the same graph, it's going to look smaller like this right here. Now, finally, we also get to the uh, Relu. And the Relu function is that it's 0 when x is negative and increasing linearly when x is positive right here. So, I plot in this in the cell right here. I create a number of equal space, 1000 equal number between minus 10 and 10. And then I compute the Relu using this function right here, maximum of 0 or x. So when x is minus, it becomes 0. So here we plot x and y and give it a title Relu right here. And then for the derivative, you can see right here, right? When x is less than 0, it's going to be 0. And then for this right here, when x is positive, it's going to be 1. So this one, this one right here is plotting x and plotting that condition right there. So these are some of the example of derivative, starting with the simple polynomial to the activation sigmoid and Relu. Hope you found this helpful. But please give a thumb up, give a like, give a heart, subscribe, and have a good day.